Welcome back to the deep dive. Okay, today we're tackling a really interesting one, N-Acetyl Semax Amidate. It's one of these highly engineered research peptides you hear about.
That's right. And it's not just, a slight variation. It's specifically designed, chemically armored, you could almost say.
Armored, I like that.
Yeah.
So our mission today is to really get under that armor, understand what N-Acetyl Semax Amidate actually is.
Yeah, with those modifications, the N-acetyl bit, the amida bit, what they actually do, why take Semax, which is already pretty interesting, and give it this chemical upgrade?
And crucially, what are the trade-offs? What does that armor cost, functionally speaking?
Exactly. It's always a balance in biochemistry.
So for you listening, the goal here is clarity. We want you to walk away understanding the thinking behind these chemical caps, how they're meant to make the molecule, well, tougher, last longer in the body.
And how that affects what it actually does in the brain, or at least what the preclinical research suggests it does, the benefits, and like we said, the potential downsides.
Okay, so before we get to the amidate part, let's define the base molecule, Cmax. What is it?
Right, so Cmax itself is synthetic. It's a heptapeptide that just means 7 amino acids linked together.
7 amino acids.
Tiny. Very small. And it's based on a natural hormone fragment, specifically ACTH410. ACTH is adrenocorticotropic hormone, big player in the stress response system.
But this is just a tiny piece of it, the 4 through 10 amino acid section.
Exactly. And that small fragment, even naturally, has some neuroactivity. But the synthetic Cmax was designed to enhance that and, importantly, make it last longer.
Okay. So even the original Cmax had stability design into it from the start. It wasn't just the raw, natural fragment.
Precisely. The raw ACTH410 fragment would get chewed up by enzymes almost instantly in the body. So when scientists created Cmax, they added a tail, a specific sequence, ProGlyPro or PGP.
PGP. And that helps it resist breakdown.
Yeah, that C-terminal PGP sequence provides a certain amount of built-in resistance to some common peptidases. Those are the enzymes that break down peptides. It helps it survive a bit longer.
Okay, so Cmax itself is already an engineered peptide designed for some stability, which I guess begs the question, why the extra armor? Why go further and create N-Acetyl Semax Amidate?
That's the perfect lead-in to, well, section 1, the chemical upgrade. This is where the heavy-duty engineering comes in.
Right, the structure and stability modifications.
N-Acetyl Semax Amidate, it's all about maximizing that stability, maximizing the half-life in the body. And it does this with 2 very specific chemical changes, like caps on both ends of the peptide chain.
Caps on both ends. Okay, let's break them down. The front end, the N-terminus.
Right, the N-terminus, that's the beginning of the peptide chain. It normally has a free amino group, an NHRS group. On N-Acetyl Semax Amidate, that group, specifically on the first amino acid, methionine, gets an acetyl group attached.
So N-acetylation. It sounds like putting a chemical helmet on the front.
That's a great way to think about it. It chemically blocks or neutralizes that free amino group.
Okay, that's the front. What about the back end, the C-terminus?
The C-terminus normally ends with a free carboxyl group, COH. In N-Acetyl Semax Amidate, this is converted into an amide group, CONHO. That's called amidation.
So a helmet on the front and maybe sealing off the back door.
Pretty much. You've got N-acetylation at the start and amidation at the end.
So why do this? What's the chemical thinking? Why are those free amino and carboxyl groups liabilities?
It comes down to those enzymes again, the peptidases. They're like molecular scissors floating around looking for specific places to cut peptides.
And those free ends are prime targets.
Absolutely. There are specific enzymes called aminopeptidases that recognize and attack that free N-terminal amino group. They start chopping the peptide up from the front.
Okay, makes sense.
And then you have carboxypeptidases that do the same thing, but they recognize and attack the free C-terminal carboxyl group. They chew it up from the back end.
So the acetyl group at the N-terminus basically hides that spot from the aminopeptidase.
Exactly. It changes the chemical structure so the enzyme doesn't recognize it or can't bind effectively.
And the amide group at the C-terminus does the same for the carboxypeptidases.
Precisely. It blocks their access point. So instead of just relying on the PGP sequence for a bit of structural resistance like in regular Cmax, these caps provide direct chemical shielding.
It sounds much more robust, like
Yeah.
locking the doors instead of just having strong walls.
It is. We see this strategy used with other peptides too. Just adding N-terminal acetylation alone can sometimes increase a peptide's half-life dramatically, maybe from minutes to hours. We're talking several-fold increases in how long it sticks around.
Wow. And that increased lifetime in the body, that stability, must have big implications for how it works, right? better bioavailability.
Definitely. If it's not getting broken down as quickly, more of the administered peptide can actually survive to reach its target tissues, potentially including the brain.
So greater metabolic stability means it can circulate longer.
Right, which improves its chances of being absorbed, say, through nasal administration, or potentially crossing the blood-brain barrier if it's designed to do that. A longer half-life means more opportunity to get where it needs to go.
And for researchers, that could mean achieving the desired effect with maybe a smaller dose or less frequent administration compared to the original Semax.
That's the potential benefit, yes. More bang for your buck, pharmacologically speaking, because it's just more durable in the system.
Okay, so the key takeaway on structure seems clear. N-Acetyl Semax Amidate is built for durability. It's designed to last longer and potentially be more potent because it hangs around.
That's the core idea behind the modifications. Enhanced stability, longer circulation.
Which brings us neatly to Section 2. What does it do once it gets there? How does this stabilized peptide interact with the brain? Let's talk mechanisms.
Okay, mechanisms. There are a few key areas, but probably the most talked about is its effect on neurotrophic factors. Think of it as influencing the brain's own growth and repair signals.
The miracle grow effect you mentioned earlier, Focus 2.1, neurotrophic factor modulation.
Exactly. And the star player here is BDNF, brain-derived neurotrophic factor.
BDNF is huge in neuroscience, critical for learning, memory, neuronal survival.
Absolutely critical. And the data on Semax, and by extension we assume its stabilized analog, shows a pretty significant effect here. A single dose of Semax has been shown to cause a measurable rise in BDNF levels, particularly in the hippocampus.
The hippocampus, right in the memory center of the brain. So it's not just a general boost, it's targeted.
It seems to have a pronounced effect there, yes. And it doesn't just increase the levels, it also seems to activate BDNF's main receptor, which is called TRKB.
TRKB receptor activation. So it's not just making more BDNF available, it's also making the cells more receptive to it.
It's like turning up the volume and pressing the play button. Activating TRKB sets off a whole cascade of signals inside the neuron.
What kind of signals?
Well, downstream, it influences things like CREB, that's a transcription factor. When TRKB is activated, it ultimately tells CREB to go into the cell nucleus and switch on the genes responsible for making more BDNF protein.
Ah, so it's actually stimulating the cell's own production machinery for BDNF. It's a positive feedback loop almost.
You could see it that way, yeah. It gets the ball rolling and encourages the cell to keep making its own growth factors.
That's pretty sophisticated. Is it just BDNF, or does it affect other growth factors too?
Research, especially in models of brain injury like stroke, suggests it's broader than just BDNF. Cmax has been shown to upregulate the transcription, the gene expression of other important neurotrophins too, like NGF, nerve growth factor, and NT3, neurotrophin 3.
NGF and NT3. Also key for neuron health and survival, right?
Very much so, especially important for different types of neurons. So the picture that emerges is one of broad neurotrophic support, particularly under conditions of stress or injury.
And this whole BDNFT-RKB signaling pathway, that's the biological basis for synaptic plasticity, isn't it? The brain's ability to adapt, learn, form new connections.
That's the direct link. Strengthening synapses, helping neurons survive, creating new connections that is learning at the cellular level. So this mechanism provides a strong rationale for the reported cognitive benefits.
Okay, that makes a lot of sense, boosting the brain's own growth and learning machinery. What about more immediate effects, like on alertness or mood? That brings us to Focus 2.2, monoaminergic modulation.
Right, the monoamines. We're talking mainly about serotonin and dopamine here. Cmax seems to act more like a modulator than a blunt instrument.
Modulator, meaning?
Meaning it influences the systems, but maybe not in the way a typical drug might, like an SSRI or a stimulant. With serotonin, for instance, studies in rodents show Cmax significantly increases serotonin turnover.
Turnover, not just levels, but how quickly it's being used and replaced.
Exactly. It suggests the serotonin system is more active, more dynamic, and since serotonin is heavily involved in mood, anxiety, maybe even things like impulse control.
Increased turnover could potentially support emotional regulation or stability. It reminds me of Semax, another peptide sometimes mentioned alongside Semax.
There's definitely overlap. Slank is perhaps better known for its anxiolytic or anti-anxiety effects, and it's also related to ACTH fragments. So modulating serotonin turnover fits that picture.
Okay, so potential effects on serotonin. What about dopamine? That's the one everyone associates with focus, motivation, reward. Does Cmax boost dopamine?
This is a really important point of nuance. Based on the research, Cmax does not seem to significantly increase baseline dopamine levels on its own.
It doesn't. So it's not acting like a typical stimulant in that sense.
Correct. If you just give Cmax to an animal, you don't necessarily see a big surge in dopamine in the brain regions you might expect, like the striatum.
It's often discussed in the context of cognitive enhancement and focus. If it's not directly boosting dopamine, how does that work?
This is where the modulator idea really comes into play. While it doesn't raise baseline dopamine, it appears to change how the dopamine system responds to other inputs.
How so?
Studies where Cmax was given alongside a classic stimulant, like amphetamine, found something interesting.
Okay.
Cmax significantly amplified the effects of the amphetamine. It led to a much greater release of dopamine and more pronounced behavioral stimulation than the amphetamine caused on its own.
Whoa. So it's not pushing the gas pedal itself, but it's making the engine much more responsive when the pedal's pushed.
That's a fantastic analogy. It seems to potentiate the stimulated dopamine release. It might be doing this by affecting dopamine storage in vesicles, or maybe influencing reuptake transporters. The exact mechanism isn't fully pinned down.
But the outcome is a dopamine system that's primed for a stronger response when activated.
Exactly. So you might get enhanced focus or cognitive arousal, especially under demanding conditions, but without the constant direct dopamine elevation you'd get from a standard stimulant. It's a more subtle, maybe more efficient way of tuning the system.
Fascinating. It's like optimizing the infrastructure rather than just flooding the streets.
Well put. It supports cognitive arousal and potentially emotional balance without being a primary stimulant itself.
Okay, so we have neurotrophic support, monoamine modulation. What about protecting the brain itself?
Yeah.
Focus 2.3, anti-inflammatory and neuroprotective signaling.
This is another really crucial aspect, especially when looking at models of brain injury like stroke. After an injury, there's often this damaging cascade of inflammation that can actually cause more harm than the initial event.
Secondary damage.
Precisely. And Cmax seems to intervene quite effectively here. Studies looking at gene expression in the brain after an induced stroke show a really clear pattern.
What kind of pattern?
A shift away from inflammation and towards protection and repair. Cmax actively suppresses the expression of key pro-inflammatory genes.
Like which ones?
Things like interleukin-6, IL-6, tumor necrosis factor alpha, TNF-alpha. These are major drivers of the inflammatory response in the brain. Cmax helps to quiet them down.
So it's dampening that harmful secondary immune reaction?
Yes. But it's not just shutting things down. At the same time, it's enhancing the expression of genes involved in neurotransmission and essential cellular signaling pathways.
So it's putting out the fire and helping to rebuild the communication lines simultaneously.
That's the dual effect observed. It shifts the brain's molecular profile towards a less inflammatory, more pro-survival, pro-communication state.
And the outcome of that in animal models?
The outcome is significant. Reduced loss of brain tissue in the damaged area, less secondary damage spreading, and ultimately better recovery of cognitive function, motor function in the animals treated with Cmax.
That anti-inflammatory signature seems incredibly valuable then, especially for recovery research.
It's a major component of its neuroprotective effects, absolutely. It helps limit the damage and creates a better environment for the neurotrophic effects we talked about earlier to actually foster repair.
Okay, this is painting a really compelling picture at the molecular level. BDNF, neurotransmitter modulation, anti-inflammation. Now let's translate that. Section 3, preclinical effects. What does this actually look like in terms of behavior and function in studies?
Right, let's connect the mechanisms to the observable results. The most direct link is effect 3.1, learning and memory enhancement.
Stemming from that BDNF boost, presumably.
That's the strong hypothesis. And we see it quite clearly in specific behavioral tests. For example, passive avoidance tasks.
Okay, remind us how passive avoidance works.
Sure. Basically, you put an animal, usually a rodent, in a brightly lit area connected to a dark chamber. Rodents naturally prefer the dark, but when they enter the dark chamber, they receive a mild, unpleasant stimulus like a small foot shock.
So they learn to associate the dark chamber with something bad.
Exactly. Then, on a later test, you measure how long they hesitate before entering the dark chamber again. It's a measure of fear memory, essentially. Longer hesitation means better memory of the bad experience.
And what did Cmax do in these tasks?
Cmax-treated animals showed significantly longer latencies. They hesitated much longer before re-entering the chamber. They also retained this memory for longer periods compared to control animals.
So clearer, stronger, more durable memories formed in healthy animals.
That's what the data suggests, yes. Enhanced learning and memory consolidation.
That's impressive on its own. But what about in situations where memory is already impaired?
Yeah.
Like after brain injury?
This is where it gets even more interesting, perhaps. In studies using animals with induced brain damage models of stroke or other injuries that impair cognitive function, Semax showed remarkable restorative effects.
Restorative how?
Animals that were performing poorly on memory tasks after the injury showed significant improvement when treated with Semax. In some cases, their performance was restored to levels close to that of uninjured, healthy animals.
Wow. So it's not just optimizing a healthy system, it's actively helping to repair or compensate for damage to bring function back online.
That really underscores the potential impact of that combined neurotrophic and anti-inflammatory action. It seems to facilitate functional recovery.
That's incredibly powerful evidence. Okay, moving beyond just memory, what about broader neuroprotection, effect 3.2, neuroprotection and restoration? You mentioned it helps reduce tissue loss in stroke models.
Yes, and we can see protective effects even at the cellular level. In vitro studies, experiments done in cell cultures outside a living organism show Semax can protect neurons from various kinds of stress.
Like what kind of stress?
Things like oxidative stress, which is damage caused by reactive oxygen species or free radicals, Semax seems to help cells withstand that. It also shows protective effects against toxicity from certain heavy metals.
Okay, so protection in a dish. Does that translate to living systems?
It appears to. As we discussed, in vivo and living animal models, particularly in stroke models, treatment with Semax leads to a quantifiable reduction in the size of the infarct. That's the area of brain tissue that dies due to lack of blood flow.
Less dead tissue. That's a very concrete outcome.
Very concrete. And that physical preservation of brain tissue directly correlates with better behavioral outcomes, improved motor function, better cognitive scores after the stroke event in the treated animals compared to controls.
So the protection is measurable both structurally and functionally.
Correct. It's a combination of limiting the initial damage via anti-inflammation and then promoting survival and repair via neurotrophic factors.
All right, so taking all this together, the memory enhancement, the neuroprotection, the neurotransmitter modulation, what does the overall behavioral profile look like? Effect 3.3, behavioral support.
Well, the profile seems geared towards enhancing function without causing dysfunction, if that makes sense.
Meaning?
Meaning it supports cognitive processes like learning and memory, and it seems to promote a state of focused alertness, possibly through that dopamine modulation we talked about.
Right, potentiating the response.
Exactly. But critically, it doesn't seem to induce the kind of overstimulation, anxiety, or agitation that you might get with more direct stimulants that just flood the system with dopamine or norepinephrine.
So enhanced cognitive readiness, maybe, but without the jitteriness or negative side effects.
That seems to be the profile suggested by the preclinical work, a state of enhanced cognitive capacity and perhaps emotional stability, rather than just being amped up. It facilitates performance without forcing it in an unnatural way.
Okay, this all sounds incredibly positive. Highly stable, promotes brain health and function, protects against damage. It sounds almost too good to be true, which usually means
there's a catch, or at least a trade-off. And that brings us squarely into Section 4, the trade-offs, stability versus specific activity.
right, because modifying a molecule, adding those chemical caps, doesn't just affect stability, it changes the molecule itself.
Fundamentally, those caps, the N-Acetyl group and the C-terminal amide, while great for protecting against enzymes and extending half-life.
They might also interfere with some of the other things the original peptide could do.
Precisely. They can alter how the peptide interacts with its biological targets or performs other specific chemical functions.
Okay, so what specific function might be compromised in N-Acetyl Semax amidate compared to the original Semax?
The main one that comes up in the literature relates back to something we touched on briefly, metal binding and antioxidant activity.
Ah, okay. You mentioned Semax can protect against heavy metal toxicity in cell cultures. How does it do that?
Well, the original Semax peptide, importantly, has that free N-terminal amino group. And that free amino group, along with potentially other parts of the peptide backbone, allows it to act as a chelator.
A chelator, meaning it binds to metal ions.
Exactly. It can grab onto metal ions like copper, QO, and zinc, Ziensor. These metals are essential in trace amounts, but they can also be toxic if they're not properly managed or if they participate in unwanted chemical reactions.
But generating free radicals.
Yes, particularly copper. Copper ions can catalyze reactions that produce highly damaging reactive oxygen species, that's oxidative stress. Copper is also implicated in the misfolding and aggregation of proteins like amyloid beta in Alzheimer's disease.
So, by binding or chelating copper, the original Cemax could potentially prevent some of that damage, acting as an antioxidant in that specific context.
That's the idea. By sequestering the copper ion, it stops it from participating in those harmful reactions. This metal binding ability is thought to contribute significantly to Semax's neuroprotective effects against certain types of insults, especially those involving metal dysregulation or oxidative stress.
Okay, but how does N-Acetyl Cemax Amidate lose this ability? What's the specific consequence of the modification?
It comes down to that N-acetylation. Adding the acetyl group onto the N-terminal amino group chemically blocks it.
Blocks the very group needed for chelation.
It seems so. The specific chemical geometry required for Semax to effectively coordinate and bind copper ions appears to depend heavily on that free alpha amino group at the N-terminus when you acetylate it.
You break the lock, essentially. You change the shape needed to grab the copper.
You disrupt the necessary binding site geometry. So while the acetylation provides stability against imidopeptidases, it comes at the cost of significantly reducing or potentially even eliminating the peptide's ability to chelate copper effectively.
Wow. So the N-acetyl version might be less effective as a direct antioxidant, specifically against metal-induced damage.
That's the implication suggested by some studies. Research looking directly at copper binding and protection against copper-induced toxicity found that N-acetylation diminished this protective effect.
That's a really significant trade-off. If a key part of Cemax's benefit is mitigating metal toxicity or related oxidative stress,
then the N-acetylated version might be less suitable for research focused specifically on those mechanisms.
So this forces a choice for researchers, doesn't it? Which version to use depends entirely on what you're studying.
Absolutely. It's not that one is universally better. They are different tools for different jobs.
If your primary goal is to maximize the duration of the BDNF boosting effect or the monoamine modulation, and you need the peptide to circulate for as long as possible,
then N-acetyl Cemax Amidate, with its superior stability and potentially better bioavailability, might be the preferred choice. You prioritize longevity and systemic exposure.
But if you're investigating, say, Alzheimer's models where copper dyshomeostasis and amyloid interactions are central, or specific types of oxidative stress,
then the original Cemax, despite its shorter half-life, might be more valuable because it retains that crucial metal-binding antioxidant capability linked to the free N-terminus. You prioritize that specific chemical activity.
It really highlights how subtle chemical changes can have major functional consequences.
It does, and we should also briefly mention the C-terminal amidation. While its primary role is stability against carboxypeptidases, removing the negative charge of the carboxyl group also changes the molecule's overall charge distribution.
Which could also affect how it binds to receptors or interacts with other molecules.
Potentially, yes. It adds another layer of difference between the parent peptide and the N-acetyl amidate version. It's not just about stability, the inherent properties are altered.
So the takeaway here is, the armor provides longevity, but might disable a specific special weapon, like metal chelation. Researchers need to pick the right tool for their specific research question.
That sums it up perfectly. Know your target, know your mechanism, and choose your analog accordingly.
Okay, that detailed look at the trade-offs is crucial context, which leads us to our final section, Section 5, regulatory context, summary, and the final thought.
And the regulatory context is absolutely non-negotiable here. We need to be crystal clear about the status of these substances.
Yes, the source materials and indeed the suppliers of these kinds of research peptides are very explicit about this.
Extremely explicit. Peptides like N-acetyl Semax Amidate are sold and intended strictly for laboratory research purposes only.
Let's emphasize that again. Strictly for research purposes only.
This isn't just a suggestion. It's the legal and ethical framework governing their use. They are not drugs. They are not supplements. They are not approved for human consumption.
And there's a very good reason for that strict boundary, isn't there?
Absolutely. While the preclinical data in cell cultures and animal models might look promising, or at least interesting, that's a world away from establishing safety and efficacy in humans. These molecules haven't gone through the rigorous clinical trials required for medical approval.
We don't know the correct human dosages, the potential short-term or long-term side effects, interactions with other medications.
Or even if the effects observed in animals translate effectively to human physiology, there's a huge gap between preclinical research and therapeutic use.
So the mandatory warning is clear. These substances are not intended for human consumption. Anyone working with them must adhere to research protocols and regulations.
Full compliance is essential. It's about safety, ethics, and legality.
Okay. With that critical context established, let's quickly synthesize the main points of our deep dive. What's the nutshell version of N-Acetyl Semax Amidate?
All right. It's Semax, the neuroactive ACTH 4 to 10 fragment analog, but with heavy-duty chemical armor, and acetylation at the front, amination at the back.
Armor designed for one primary purpose: dramatically increased metabolic stability, making it last much longer in biological systems.
Right. This enhanced stability translates to potentially better bioavailability and a longer duration for its core proposed actions,
Which include
boosting BDNF production and signaling, especially in the hippocampus, modulating neurotransmitter systems, increasing serotonin turnover, and potentiating stimulated dopamine release, and shifting the brain towards an anti-inflammatory pro-survival state, particularly after injury.
but there's a significant trade-off baked into that stability.
Yes. The N-acetylation, crucial for blocking enzyme attack at the front end, likely compromises or eliminates the original Cmax's ability to chelate copper ions.
Meaning it might lose a specific metal-related antioxidant function that the parent peptide possesses.
Exactly. So researchers need to weigh the benefit of extended duration against the potential loss of that specific activity, depending on their research focus. Stability versus specific function.
A fascinating case study in peptide engineering, which brings us to our final provocative thought for you, the listener.
Okay, consider this. N-acetyl Semax amidate is derived from just 7 amino acids, a tiny piece of information extracted from a much larger complex hormone, ACTH.
And then scientists deliberately added chemical modifications to the acetylenamide caps, not for biological activity per se, but purely to help it evade the body's natural peptide-destroying enzymes.
So if we can take such a minimal biological sequence, make it synthetically durable, and have it produce these potentially profound neurological effects like boosting BDNF or modulating neurotransmitters, all while potentially avoiding the broader systemic effects of the original hormone.
Like ACTH's effects on the adrenal glands and cortisol release, for example.
What does that really tell us about the future of designing targeted therapies? Does it suggest that maybe we only need very small, very specific pieces of biological information, if we can package them correctly, to achieve highly specific and powerful effects in the brain or other tissues?
Is the future about finding these minimal effective sequences and then just building better and better delivery or stability systems around them? How much of the original complexity is truly necessary if we can engineer durability?
And thinking about that trade-off, losing the copper chelation for stability, how sophisticated will peptide design need to become to achieve both maximal durability and retain the full spectrum of desired biological activities? Are we moving towards multifunctional engineered peptides?
The quest for the perfectly targeted, perfectly durable molecular messenger. It seems like the optimization challenge is really just getting started.
Indeed. Finding that sweet spot between minimal information, maximal effect, and engineered resilience.
An absolutely fascinating area. Thank you for walking us through the chemical intricacies and functional implications of N-acetyl Semax amidate today.
My pleasure. It's always great to dive into the details where structure meets function.